Welcome to Hartman Math. Before we start talking about complex numbers, let's complete a warm-up based on vectors as well as a prior review of some trigonometry concepts. Go ahead and pause the video here, work through our 3 problems, hit play when you're ready. All right, number 1, our vector is going to be in approximations. We're doing this from trigonometry. That's not going to be exact, so we're talking about 10 times the unit vector, 10 times cosine 287 degrees, comma sine 287 degrees in our vector pointy brackets. And we're going to get about the vector 2.92 comma negative 9.56. Notice that our vector here is in i's and j's, so we probably want to respond in terms of a linear combination of those i's and j's. Step 1 is to find the unit vector here, so find the magnitude and then do the scalar division, and then multiply the entire thing by 5, and you're going to get the vector v is equal to negative 35 over root 65 times the vector I plus 20 over the square root of 65 times the vector j. Cosine alpha minus beta. So we're going to do cosine alpha, cosine beta plus sine alpha, sine beta. We're going to want sketches for both of those. Turns out that your answer is going to be 3 root 5 minus 8 all over 15. All right, we're going to start here with a brief look at lesson 6.5, the complex plane. We've got in the complex plane a real axis and an imaginary axis. So the point complex number 3 plus I is 3 plus 1i. So we're going to go positive 3 on the real axis and then up 1 on the imaginary axis. Negative 2 minus I would be left 2 and down 1. The absolute value of a complex number like 3 plus I or negative 2 minus I, also known as the modulus, is the distance between the origin and that point in the complex plane. So the definition and the absolute value is just going to be the square root of a squared plus b squared is how we could calculate that. Example number 1, plot the point in the complex plane, find its absolute value. So the negative 3 is the real part, so we're going to go left 3. Plus 1i, we're going to go up 1 in the imaginary direction. There's our point. And the absolute value of that point, or the modulus, is the square root of negative 3 squared plus 1 squared, which would be the square root of 10, and that is the distance here. Kind of think of that as a right triangle, and use the Pythagorean theorem. 3 squared plus 1 squared does make the square root of 10 squared. And that's where that's coming from. So on to lesson 6.6, trigonometric form of a complex number, which is going to enable us to do a lot more things with that complex number. So again, we've got our imaginary axis, we've got our real axis. So if we're talking about a point in the complex plane, we've already said that the absolute value of the complex number is the square root of a squared plus b squared, and that's going to be defined to be this distance r. And then we've also got the trig angle theta measured from the positive side of the, used to be the x-axis, or now the real axis is going to be the theta. Remember, this is based on the fact that the square root of negative 1 is I by definition. So the question is, well, if that's true, what's the square root of I? And we don't yet have enough knowledge to be able to answer that. Maybe we will at the end of the lesson. So the trigonometric form of a complex number, z, the complex number, is equal to r, that distance, which we're able to calculate, times cosine of theta, the trig angle, plus I times the sine of theta. And we say that r is the modulus and theta is the argument of that complex number z. So write this complex number in trigonometric form. So it might be a good idea to kind of think about sketching it in that complex plane. Write 1 down root 3. In which case, what's the r? We could do just the square root of a squared plus b squared. We could do Pythagorean theorem. Doesn't matter, but either way, you're going to get 2. And then theta, think of this in terms of very close to being unit circle. Remember, in a unit circle, we would have something that the coordinate is 1/2 comma negative root 3 over 2. If we just multiply both those by 2, we're still looking at the same angle. It's going to be 5 pi over 3. So our z, complex number in trig form, r times cosine theta plus I times sine theta. So 2 times cosine 5 pi over 3 plus I sine 5 pi over 3 is that complex number in trig form. Example number 2. We got a complex number in trig form. Write it in standard form, a plus bi. All we really need to do is evaluate and simplify. So what is the cosine of 150 degrees? Thinking quadrant 2, long left, short up. So the coordinates for 150 degrees in the unit circle are going to be negative root 3 over 2, comma, positive 1/2. So negative root 3 over 2 here, positive 1/2 there. Now we just need to distribute in 4 root 3. And there's our number in standard form. Taking two complex numbers and multiplying or dividing. Okay, this is how to do it in when they are in trig form. Z1 times Z2, complex number 1 times complex number 2. You just need to multiply the two r values and then multiply that by the cosine of the sum of the angles plus I times the sum of the angles. And then kind of similarly and somewhat connected, if we're dividing our complex numbers, we divide the r's and it's times cosine of subtract the angles plus I times sine subtract the angles. So these are both in trig form. Go ahead and multiply these together. Remember, we would multiply the two r values, 10 times 6, times cosine of, add the two angles. So we're talking about 18 pi over 2, I'm sorry, 18 pi over 12. I think we could reduce that. Plus I sine, and again, add the angles, same angle. There's our setup. Simplify. Now let's see if we can go even further, get this maybe into, well, if we wanted it in trig form, there it is. If we wanted it in standard form, we can go further. Cosine of 3 pi over 2 straight down, so that's going to be 0 and negative 1. And in standard form, it'd be negative 60i. If you wanted your answer in trig form, it was right here. Dividing, this time in degrees, but no problems there. We would divide the two r values, so 12 divided by 3 times cosine of, subtract the two angles, 70 minus 25 in terms of degrees. We can simplify, there would be our answer in trig form. If we want it in standard form, we can evaluate. We know that this is going to be root 2 over 2, so is that, root 2 over 2. Distributed into 4. 2 root 2 plus 2 root 2 times I would be standard form for that complex number. On to de Moivre's theorem. De Moivre. And what this is allowing us to do is to take a complex number in trig form and raise it to a power. So in terms of standard form, if we were raising maybe a complex number to the second power, it wouldn't be that difficult to do. But if we're talking about raising to the fourth power, sixth power, something like that, that's a lot of multiplication to do. De Moivre's theorem is much simpler, where it's saying that if I want to take a complex number z and raise it to a power of n, all I got to do is raise r, its r value, to the power of n and multiply it by cosine of the angle times the n, plus I sine the angle times the n. So if we were doing this one, I definitely wouldn't want to have 6 factors and do all that multiplication. I would probably want to do it with the Moivre's theorem, start into trig form. So I want to find the z first. So let's think about this. Okay, we'd have to find the r first. So the square root of -1 squared plus 1 squared. So I think we're talking about the square root of 2. And then our angle is left 1 in terms of a sketch and up 1. That seems like an isosceles right triangle, so one of our 45 degrees, or pi over 4s. I think we're talking about quadrant 2 being 3 pi over 4. So our trig form is going to be the square root of 2 times cosine 3 pi over 4 plus I sine 3 pi over 4. That's the hard part, because de Moivre's theorem is actually really easy. Now to do z to the 6th power, we're going to do root 2 to the 6th power times cosine of 3 pi over 4 times that 6. 3 pi over 4 times the 6. So root 2 to the 6th power would be the same as root 2 times root 2 squared and then cubed. So 2 to the 3rd power would be 8 right there. And our angle here, so we're talking about 18 pi over 4 or 9 pi over 2. And let's think about where that would be in terms of a coterminal angle. So 1 pi over 2 on top, 2, 3, 4, 5, 6, 7, 8, 9 back on top. So 9 pi over 2 is coterminal with 1 pi over 2 straight up. So cosine is going to be 0. Sine of 9 pi over 2 is going to be 1. So z to the 6th power, here's our z right there, 8 times 0 plus 1i is 8i. And we're going to finish with probably the more complicated part. We just saw raising a complex number to a power. What about taking the roots of complex numbers? So this is going to bring us back to that initial question, what is the square root of I? So if we were to look at an equation like x to the 6th power equals 1, as that's going to be a 6th degree equation, it's going to have 6 solutions. To find all those, we could do all the factoring and all of that stuff. And we can also use the idea of the roots of complex numbers that we are going to take to find all of them. If we just take a simple 6th root at the beginning and go plus or minus, we're not going to get all of them, all of the complex ones. So here's our formula. Z, our root, is going to be, whatever root we're taking, if we're taking nth root, is the nth root of the r times cosine of our theta that belongs to the z plus 2 pi k divided by n. Again, n is whatever root you're taking, and so on. And then we're going to plug in values for k starting at 0 and then all the way up to 1 less than the exponent. So like that last one we were talking about, we're finding the 6th roots. We're going to plug in 0, 1, 2, 3, 4, and 5. And that's going to get us all 6 of the roots. Example number 8, find all of the 4th roots of -16. So another way of asking a very similar question is the equation, let's solve x to the 4th equals -16. Find all of the 4th roots. So we're finding the 4th roots of -16. -16 is going to be our z, our complex number. We want to write that in trig form. A sketch is always helpful. So think of this in terms of the complex plane. Imaginary axis, real axis. Where is -16? It's entirely real and it's going left. So in terms of a sketch, it's going left 16 units. Straight left is the angle pi. Think of it in terms of a sketch. So So there's our z, 16 times cosine of pi plus I times the sine of pi. Now we want to find all four of the roots. Talking about fourth roots, so we're going to take the fourth root of the r, and we're going to cosine of, theta is going to be pi. Pi plus 2 pi k divided by, we're taking fourth root, so it's going to be 4. So there's our setup. And at that point, we just begin evaluating that by plugging in 0, 1, 2, and the last one will be 3, which is always finished one less than the root that you're taking. So we'd start by plugging in a 0, which makes this disappear, this disappears. We're going to talk about cosine of pi over 4. We know the fourth root of 16 is going to be 2. So we'll start with k is 0, and that's what we get. And in some instances, you might just want the trig, it in trig form, and that would be good enough. If we want it in standard form, we would evaluate root 2 over 2, root 2 over 2, distribute the 2. For k is 1, we're going to get pi plus 2 pi, so 3 pi over 4. So everything's the same except now our angle is 3 pi over 4. And again, if we wanted just trig form, good enough right there. For evaluating, we're going to talk about, that's going to be negative, so negative root 2 plus root 2i. K is 2, so we're talking about 4 pi plus pi, 5 pi over 4. You can kind of see the pattern now establishing here. Quadrant 3, left and down, so both of those are going to be negative. We finish with k is 3, clearly pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Notice that those are all equally spaced. And we get our final root of the fourth roots. All right, example number 9. Solve the equation x squared equals I. X is going to be the square, all the square roots of I. So we're going to get to that question that was asked at the beginning. And we're talking about all of the square roots. So there's going to be 2 of them. So again, this is what we're taking the root of. So that's our z. So think about, where is I in the complex plane? Straight up 1 unit. So write I in trig form, 1 unit up. So there's our r. And we're going up, so it's pi over 2. Now we're going to take the second roots of that. So we're going to take the square root here. We're going to do cosine of pi over 2 is our angle, so pi over 2 plus 2 pi k over taking second roots. So now we need to evaluate that starting at k equals 0, where we would get pi over 2 gone, divided by 2 makes pi over 4. So answer in trig form here. If we want to go standard form, just use our unit circle knowledge, root 2 over 2 plus root 2 over 2i. So one of the square roots of I is right there. Other one, we now do k is 1, so pi over 2 plus 2 pi is going to be 5 pi over 2. Divided by 2 is 5 pi over 4. Now we're in quadrant 3, so we're going to be negative here, negative here. And those are going to be the roots of I, both of the square roots of I. That's it for today. I'll see you next time.